Okay, last time we were converting -3, 3 to polar coordinates, and we found r to be 3 root of 2. Now we're going to find theta. Okay, so what is theta for this particular point, right? Well, what we can do is we can recall something else that we've already known. We know that tangent theta is equal to y over x, right? That is something that we've done before because that's sine over cosine, right? So if we think about our y over x, we know that tangent for some theta is 3, which is y, over -3, which is -1, right? Now the angle that's in quadrant 2, whose tangent is -1, right? Remember we said that this angle is in quadrant 2, so the angle in quadrant 2 with with tangent -1 is 3 pi over 4. How did I come up with that? Well, I know that tangent of 3 pi over 4 is the same thing as sine 3 pi over 4 over cosine 3 pi over 4, which is root 2 over 2 over root 2 over 2. I'm sorry, negative on the bottom, that's a -1, right? So that's how I'm coming up with that. So that is the angle in quadrant 2 whose tangent is -1, the only one, so that's my theta. Theta is 3 pi over 4. So we can say then that -3, 3 is the same thing as 3 root 2, that's my r, comma 3 pi over 4. Okay, so we've converted from rectangular to polar that way. All right. Now we can also use the ideas that x equals r cosine of theta, y equals r sine of theta, r squared equals x squared plus y squared, and again that the tangent of theta equals y over x, to change equations from one set of coordinates to the other. And this is something that's often helpful in calculus. Like I said, some equations are easier to deal with if they're in polar coordinates, and some are easier in rectangular coordinates. So it's kind of a nice thing to be able to know how to do. So we're going to take an equation in rectangular coordinates, that's x squared plus y squared equals x, and we're going to put it into polar coordinates instead. So it's kind of like you're switching the variable, really, right? But it's more than a variable. They actually stand for coordinates. We said earlier that x squared plus y squared is equal to r squared, right? So I have r squared equals x. So now it's kind of halfway in between polar and rectangular, okay? Now I also know that x, though, is r cosine of theta, right? And since I know that r is not 0, right? If r were 0, then my point would just be the pole, right? And it doesn't actually have coordinates in this situation because I know that my origin is not this, okay? So now I know that r cosine of theta is equal to r squared. If I want to, I can divide both sides by r, and that leaves me with r equals cosine of theta. And that is my equation that is now in polar coordinates. I know it's in polar coordinates because it has r and theta instead of x and y. Okay, let's look at a second problem. We're going to take the equation r equals 4. This is in polar coordinates, right? So this r is meaning the r that is the first coordinate of a polar coordinate, okay? We're going to do a little trick, which is we're going to square r. We're going to say, oh, r squared is equal to 16, okay? Because r is 4. Now I also know that r squared, is x squared plus y squared. So I end up with the equation x squared plus y squared equals 16. Yeah. So it turns out that that's a circle. Yeah. So r equals 4 is a circle. Think about it for a second. If we have our polar grid, here's our circle of radius 1, circle of radius 2, circle of radius 3, I'm not making this very good because they should be even, circle of radius 4, right? So every point on this radius satisfies the equation r equals 4, right? Because all of them have their first coordinate as 4, their r coordinate as 4, right? So it makes that circle. Okay, so that's the idea of what we're doing here. Okay, well, let's look at another example. We can say r cosecant of theta is equal to 8. Let's say that's an equation. Okay, so now it's in polar coordinates. I want to put it into rectangular coordinates. First of all, we know that cosecant is 1 over sine. So cosecant, so we have r times cosecant is the same thing as r times 1 over sine. Okay, that's the same thing as r over sine theta is equal to 8. Okay, so I've got my theta. I'm sorry. Now I know that y, if I want to go into rectangular coordinates, is r sine theta, right? So it turns out that y over r is sine theta. So what I'm going to do is I have the r already from the equation. I'm going to replace this sine theta here with y over r because it's equal to it. Okay? And then if I flip and multiply, because I'm dividing by a fraction, I get r squared over y is equal to 8. Again, here I'm halfway in between polar and rectangular coordinates. Okay? Well, what do we do with the r squared? Ah, r squared is x squared plus y squared, remember? Over y equals 8. So I'm pretty much done. This is an equation in rectangular coordinates. But what does this look like? What is this, right? If I were to graph it, what would it be? All right, well, let's multiply both sides by y. We get x squared plus y squared equals 8y. And then I say, oh, look at this. This is a circle. How do I know that? Well, it's got x squared and y squared in it. And I also have this minus 8y, right? Do you remember completing the square of a circle? Well, the x squared is fine. If I'm going to leave it the same. If I want to complete the square for the y squared minus 8y, remember what we do. We take, go away. No, go away. Okay, we take half. Oh my God. Hold on, my pen is being all weird. Okay, we take half of negative 8, that's the b, and we square it. So that's a negative 4 squared, which is 16. So I'm going to add 16 on the left-hand side, and of course, I also have to add 16 on the right-hand side. So I get x squared plus, we factor this guy, y minus 4 squared equals 16. So notice it's a circle with center 0, 4, and radius 4. Okay, so the graph of that circle in polar coordinates would look like r cosecant of theta equals 8. Okay, and then we could draw that graph, of course. Okay, we're going to graph just one polar equation, and generally when you want to graph it, you change it from polar coordinates to rectangular coordinates, just because we're really good at graphing rectangular coordinates. So it's easier for us to think of it that way. So if I had the equation r sine theta equals 2, well, I know that r sine theta is the same thing as y. So this equation is really just y equals 2, right? That's a vertical line. No, I'm sorry, it's not a vertical line. It's a horizontal line, pardon me. I was thinking horizontal, but I wrote vertical. It's a horizontal line through the y-axis at 2, right? Because 2 satisfies that line, every point on that line. So here is we still want to put it was given to us as a polar equation. So we're going to graph it on a polar coordinate system, a polar grid. So notice if I have these circles, this is radius 1, radius 2, which is really the same thing. It coincides the same with the rectangular coordinate system at 2. Okay, so here is r sine theta equals 2. It's a horizontal line through 2, but it's on the polar grid. All right, so basically the idea to graph right now, for us, to graph polar equations, we replace r and theta with their equivalents using x equals r cosine theta and y equals r sine theta, right? And also x squared plus y squared equals r squared. And every once in a while, tangent theta equals y over x, although it's not as useful unless you're trying to get to polar coordinates from rectangular and you know y over x and they're somehow in a good ratio to each other. Anyway, you do that to find out which type of equation, for us, again, it's either going to be a circle or a line in rectangular coordinates that it would be. And then you graph that circle or line. Right? Later in Calculus 2, so this is graphing polar equations for now, right? Because we're not going to do very many complicated ones. And in fact, you can ignore the second part of the section 9.2 when it starts to, kind of take a look at, crazy thing like these roses and limacons, I think they're called, cardioids and limnoscates. You're going to do that in Calculus 2. You're going to learn how to graph those using polar coordinates. But right now we just want you to be pretty comfortable and feel like you know what a polar coordinate is. All right, thanks.